exercise, not exercise, but so let's assume that we have the standard basis for this domain. It is 1, 0, 0, 1, and the new basis is composed of vectors 1, 2, 1, 1. Okay, so we have these two, and now let's try to determine what are the. I'm trying to find the space. What are these four vectors used in the polar representation? Actually, we saw this one, but I always feel I don't like to erase a lot of information. So let's assume that these are complex numbers. Then what is 1, 0 as a complex number? This vector 1, 0, if this is shown in a graph where presumably this would be the real part of any complex number set, and this would be the imaginary part of any complex number set, then 1, 0 would be equal to, this is equivalent, this is not equal, so 1, 0, it would be this number, which would be simply 1. Okay. Now, what is the polar representation of 1, 0? The polar representation of 1, 0, it is always described as r times e to the power I theta. R represents the magnitude. What is the magnitude of 1?
1.
That's good. It is 1. Then we don't write it. E to the power I times what? What is angle theta?
0.
0. Yeah, that's correct. It's 0. So it is 0. So, and what is e to the power 0?
1.
Any number to the power 0 is 1, okay?
Yes.
So equal to 1. But we can write this one also e to the power I times 2 pi. This is also correct. So when you say that the angle here is 0, you can consider also that the angle is 2 pi. Okay? So this is also true. Or we can write this one e to the power I times 8 pi. This is also possible. Okay? Anyway, so this is enough. We can always actually, for any polar representation, we can always have, if you have the angle 37, that is one value, but you can also give 37 plus 360. 37 plus 360 times 2. Okay, we did this one. What about 0, 1? What is 0, 1 in vector notation? But we want to look at the polar representation in the complex numbers plane. What is this?
1 times e.
Well, let's write first this notation. Not before writing the polar representation, let's write this representation. So we have a z, it can be written x plus jy, and this is also equal to r e to the power I theta, and this is equal to x squared plus y squared square root e to the power I theta. Now, this one is the polar representation. Okay, so let's write initially, let's write this. So, what is 0, 1? Just I, okay? 0, 1 is just I. And let's see the other vector, 1, 2. What is 1, 2? 1, 2, it is 1 plus 2i. Okay? What is 1, 1, which is the other vector? Here, 1, 1, this is equal to 1 plus I. So these are the standard representation of these four vectors that we have here on the graph. Are these clear?
Yes.
Okay, then let's continue here. So what is the magnitude, or what is r of I?
1.
1, that is true, because it's a circle with radius equal to 1 that moves like this. So this is 1, we don't write it. E to the power I, what is angle theta?
90 degrees.
90 degree. Often it looks more elegant if you write it pi over 2. But it's the same thing. E to the power I times 90 degrees, that's fine. Or we can write this equal to pi over 2 is 3.14. So this is equal to e to the power I 1.57, but this is radian, okay? So if you change the settings in your calculator between radians and degrees, these are different ways that you can write it down. That is good. But we can also write this one also like this. This can be equal to e to the power I times 1.57 plus 2 pi. What is 2 pi? 6.28, okay? Which is all, everything is the same. So then we can play along as much as we want. 1.57 plus 2 pi. So 2 pi, 6.28. Good. Let's come here. So what is the magnitude? We don't call it magnitude actually. Magnitude we call it in the vectors. We can call it what is the modulus. Okay. Modulus. What is it in this case? Any answer?
Square root of 5.
That is true. Square root of 5 times e to the power I. So what is the angle? In order to find the angle here, the angle is, so we call this one angle theta 1. This is equal to tangent inverse of y over x, okay? And this is equal to tangent inverse y is equal to 2 divided by 1. So this is 2 divided by 1. And I don't remember the numbers, but it's something like around 33, at least based on the
inverse tangent of 2, it's 63.4.
63.4, okay. This is degrees. Okay, that's good. We did it. Then let's look at this other number. So this one would be equal. What is the modulus of this complex number?
Square root of 2.
That is true. Square root of 2 e to the power I. What is the angle?
45 degrees.
45. That's true because it's 1, 1. So this side is equal to this. And it is, als je kan draait, dan brengt Barbara 45. So this is times 45 degrees, or square root of 2 e to the power I times pi over 4, or equal to 1.57 divided by 2, 0.78, okay? Square root of 2 e to the power I 0.78 radian, this is degree, okay? Yeah, so these are the representation of what they used to be bases in the real domain. Now, in the complex domain, we can interpret them as shown in here. And in fact, showing it in this way, what we can extract from here, we can extract the fundamental information regarding the rotation of the axis. How much did we need to rotate these respective axes to get this new basis? So it looks like the x-axis, it rotated by an angle of 45 degrees, and we observe it like this. And the z-axis, it rotated clockwise by an angle of 33, 23, whatever this is, 27.6, okay? So it moves clockwise by an angle of 27.6 because we do 90 minus this number. Okay. Any other question or regarding the material? Okay, let's give another short break.